Hello again. In this video, we're going to discuss an application to dynamical systems. Eigenvalues and eigenvectors hold the key to the discrete evolution of a dynamical system. A dynamical system is all about the evolution of something over time. And we will be able to use eigenvalues and eigenvectors to find the state of the system at a specific time. The example that we're going to look at today is about migration, population migration. We're going to use difference equations. So what is a difference equation? Well, let's look at that. It says if there is a matrix A such that we have this relationship, if you take A times x naught, which is our linear transformation matrix, it's going to equal x1, the next one. And then we do it again, x1 times a, to give you x2. That's called a recursion equation or a linear difference equation. So we're going to get that from this example you will see in a few minutes. So let's go ahead and read the example. Suppose demographic studies show that each year about 5% of the population, city's population, moves to the suburbs. So they have a picture of this. Here's the city, here's the suburbs. 5% go to the suburbs. And while 95% remain in the city. So that's where this comes in. Then 3% of the suburb population moves to the city. And 97%, which means 97% remains. We are ignoring, for simplicity, all other influences of the population, such as births, deaths, migration into or out of the city suburb region. So this is it. So what we're going to do, we're going to fix an initial year. Say 2014. Assume that that is given. And we're going to denote the population of the city's suburbs by that year by R naught and S naught respectively. So R naught will be the city and S naught will be the suburbs. So we're going to let X naught be the population vector, R naught, S naught. Again, R naught is the city population in 2014, S naught is the suburb population in 2014. And then we're going to, all the future years, X1 would represent 2015, X2 would represent 2016, and so forth. And what our goal is we want to describe mathematically how these vectors might be related. So I'm going to find x1. So how did I find x1? Well, I looked at the city, so let R1 be the city's population in 2015, the next year. And we know that 95% of the people from the city stay in the city, where 3% from the suburbs come over. So this is 3% of the suburbs plus 90% of the people who stay. I'm going to do the same thing for the suburbs. I look at this picture, what's coming in there. 5% from the city, comes in, and 97% stays. So I end up with x1 equals r1 s1. And I just put these in here, and then I can split this up into a matrix times x naught. We're going to call this the migration. Get that statement where M is the migration matrix denoted by this table. We can do the same thing for the next year. It would be the same formulas. R2 would still be 95% of R1 now, plus 3% of S1, and S2 would still be, here's the picture, S2, 5% comes in of R1, of the city from last year, and 97% remain the same. That's assuming that the population is the same every year. which they said in the original that it was. Each year. So we can do the same exact equation for x2, and you can see that we have a difference equation. There is x2. Or in general, x sub k plus 1 equals m times x sub k, where m is our migration matrix. So there is our m. The sequence of vectors x0, x1, x2 describes the population of the city suburb region over a period of years. So let's look at example 3. This example is in the book, if you want to follow along, in section 1.10 on page 85 and 86. So example 3 says, compute the population of the region just described above for the years in 2015 and 2016, given that the population in 2014 was 600,000 in the city and 400,000 in the suburbs. So remember, the first column was the city, this is the suburbs, that is x0. This right here, we know x1 is equal to m times x0 is what we found above. So we're taking our migration matrix, which is what we have here, and multiplying it by our x0. And then x2 is m times x1. So we take the same migration matrix, but now we take x1 to get 2016. And again, this one is the population in the city. This is the population in the suburbs. And it looks like each year people are moving away from the city into the suburbs. So now let's see how eigenvalues can help us find the long-term behavior of this dynamic system. This example now is from our section, section 5.2 in the book on page 280 if you want to follow along. This is a long example. So our first step is just to find the eigenvalues. So I'm going to try to quickly go through this. Step 1, finding the eigenvalues. So what we're going to do is we're going to look at our characteristic equation, a minus lambda I, which I wrote here. I'm going to set equal to 0 to find our eigenvalues. And so I'm going to take the determinant of that, combine the like terms. That does not look like I want to factor it, so I just use the quadratic formula. Here's my quadratic formula, where a is 1, b is negative 1.92, and c is 0.923. And I saw that this was perfect, it was rational, so I just wrote it as such, and I found the two eigenvalues. So I did part 1, there's step 1, find the eigenvalues. Step 2, it says to find the basis for the eigenspace. So that is step 2 here. To find the basis for each eigenspace, we look at what the eigenspace is, which is this equation. I'm going to solve for that equation. So again, I look at that same matrix, but now I'm going to plug in when lambda is 1. When lambda is 1, here's what I get. There's the solution. Let's go to the left a little. If you plug in lambda is 1 here, you get negative 0.5 and negative 0.3, and these stay the same. This looks like something very easy to solve. I multiplied by negative 100, and I realized these were the same, so this is just a row of zeros. And here is my solution. This is true since 5x1 minus 3x2 equals 0. x2 is free, so I just solved for x1 there, and I got that solution. I didn't feel like dealing with a fraction, so I can multiply, take any vector, multiply it by 5, for instance, and I'm going to use v1. v1 is an eigenvector for lambda. We're going to use that in the future. You'll see. So now I'm going to do the same thing when lambda is the 0.92, the other one that we found. So when it's 0.92 here, this would be 0.03, and this would be 0.05. So we solve this one the same, and we get this is the eigenspace. And what I'm going to do is pick an eigenvector. I just don't want there to be a negative here, just for simplicity. So I let x2 be -1, and I'm going to let v2 be 1, -1, and it is an eigenvector for 0.92. So now what I'm going to do is I'm going to use these two vectors, and I'm going to find my x0 in terms of these vectors. Since v1 and v2 are linearly independent, as you can see, we know they form a basis for R2. So there exists a C1 and a C2 such that C1v1 plus C2v2 equals this matrix. Try to go a little slower. So what I'm going to do is want to isolate this matrix, so I multiply both sides by the inverse, v1, v2 inverse. So then we have C1, this is an I, is equal to this equation. This is my v1, this is my v2, and if I take the inverse of that, that is invertible, that is good, times the x0. If you remember, our next x0 at the beginning of the problem was 0.6, 0.4, and we can find a C1 and C2 now that makes that happen. We're going to use this also in the future. So I'll put a little check mark there. But I found the inverse of this, which was -3 minus 8. That's why the -1/8 is there. We switch these. We put a negative there. We multiplied it out. There's the work. Finally, I want to find an explicit formula for xk. And I'm going to use all of this. And what we're going to do, here's the new stuff. Let me just get the whole thing here. v1 is an eigenvector. We saw that for lambda is 1. So we know that a times v1 is v1. And v2 is an eigenvector for 0.92. So we know av2 is 0.92 v2. And I'm just going to do this recursion formula. x1 we know is ax0. So I plug in my x0 there from above. This is what x0 was. And I can bring my a through. So we know this is just a v1, and this is a 0.92 v2. So I get that formula. I'm going to do the same thing with x2. Now I know x1 is this. So I bring in that a, and again, this is just v1. There's where that is. And this one is 0.92 again, so we get a squared. So the next one just has a cubed. Or in general, here's my formula. Notice how these stay the same no matter what we're doing, and we get a 0.92 to the k. And here it is. We have an explicit formula for x sub k. By the way, we could have used any v1 or any v2. So we just picked 2. But we got a formula. So now we can look at the long-term behavior. The long-term behavior, which is what the question was, the original question. If you go back to the original question, analyze the long-term behavior. So I'm just going to look at what happens when k goes to infinity. You know, this whole thing goes to 0 as k goes to infinity because we have 0.92. The limit of 0.92 to the k, something less than 1, goes to 0. So we have the long-term behavior is just the first term, c1, it's a 1 there, c1 times v1. So here's c1, if you look at above. Here was v1. If you multiply them together, that is our long-term behavior. So it looks like, if you remember what the x0 was, the x0 was 0.6 and 0.4. It looks like it's switching, isn't it? More people are going to the suburbs than the city.